Imagine stepping out in a city you have never visited before. The streets bend in unfamiliar directions. The buildings look similar. You are not sure which way is north or how far you are from your destination. So you pull out your phone, open a map, and within seconds, a small blue dot appears. It knows where you are. Your phone cannot see you from above. It is not connected to the sky by a wire. It does not ask anyone nearby for directions. Yet somehow, this small object in your pocket can place you on an entire planet. To understand how that happens, we have to go back to a time when GPS was not built for coffee shops or ride-hailing apps, but for a much more dangerous military problem. Let's get into it right here on Secrets of Simple Things. From maps to missiles, the story of GPS begins during the Cold War, when location was not just a convenience. For the United States military, knowing exactly where something was could decide whether a mission succeeded, a ship stayed hidden, or a missile reached the right target. In the 1950s and 1960s, navigation was still difficult in the places where it mattered most. In the middle of the ocean, there were no street signs, no roads, and no obvious landmarks. A submarine carrying nuclear missiles could not simply guess its position. A small error could become strategic. The U.S. Navy first experimented with a satellite-based system called transit. It helped submarines determine their location using signals from space. Transit was not perfect. It could not provide instant, constant positioning everywhere. But it proved a powerful idea. Satellites could become navigation tools. Then, in 1973, the U.S. Department of Defense launched the Navstar GPS program. The goal was ambitious, a system that could give precise location data anywhere on Earth at any time, in any weather. But to make that possible, they needed landmarks that did not sit on the ground. They needed guideposts flying around the planet. The landmarks in the sky. For most of human history, navigation depended on things people could see: mountains, stars, coastlines, towers, and later, paper maps. GPS works with the same basic idea, but its landmarks are not fixed on Earth. They move high above us, circling the planet again and again. The system depends on a network of satellites orbiting Earth. At least 24 satellites are arranged so that, from almost anywhere on the planet, a receiver can usually hear several at once. They are invisible signposts in the sky, constantly announcing where they are. Each satellite sends out a signal with two key pieces of information: its own position and the exact time that signal was sent. Your phone, car, or handheld GPS device is not taking a picture from space. It is listening to carefully timed satellite messages, then comparing them in the background. But knowing where the satellites are is still not enough. The real secret of GPS depends on something that sounds ordinary: time. Location is really a time problem. GPS does not directly see where you are. It works backward from time. When a satellite sends a signal, it travels through space at an extremely high speed. Your GPS receiver compares the time the signal was sent with the time it arrived. From that tiny delay, it calculates how far away that satellite is. That is the key. Your location is not guessed from one signal. It is built from several distances. Imagine standing in a park with no map. If someone tells you that you are 500 meters from a tree, you could be anywhere on a circle around that tree. If you are also 400 meters from a bench, the possible area becomes smaller. Add a third distance from a statue, and the overlapping circles point to where you are. GPS does this with satellites instead of trees, benches, and statues. People often call this triangulation, but GPS is more accurately doing trilateration. It finds your position by measuring distances, not angles. Each satellite gives one distance clue. With enough clues, your receiver can calculate latitude, longitude, and altitude. That is why GPS usually needs signals from at least 4 satellites. 3 help narrow down your position. The 4th helps correct timing, because your receiver's own clock is not as perfect as the clocks above it. But for those distances to be right, the system has to measure time with almost unbelievable precision. the clocks that keep the world in place. If GPS is built on time, then its clocks have to be almost unimaginably precise. Each GPS satellite carries an atomic clock, accurate far beyond a normal phone or car. These clocks are synchronized because the whole system depends on tiny differences in signal arrival times. And tiny really means tiny. A time error of just 1 microsecond, 1/1,000,000th of a second, can push your calculated position off by hundreds of meters. That is the strange beauty of GPS. A mistake too small for a human to feel can become a visible mistake on a map. A fraction of time becomes a distance on Earth. But even perfect clocks are not enough, because GPS has to deal with something that sounds like it belongs in a physics classroom. Einstein's theory of relativity. The satellites are moving quickly around Earth, and they are far above the planet's surface. Because of that, time does not pass for them in exactly the same way it passes for clocks on the ground. The difference is small, but for GPS, small differences matter, so the system corrects for those effects constantly. When you open a map to find your way home, your phone is benefiting from a system that quietly accounts for modern physics. At first, all this precision was not meant for ordinary drivers or pedestrians. But eventually, a military technology began moving into civilian life. From military tool to everyday habit, GPS began as a military system designed for situations where accuracy could carry enormous consequences. But in the 1980s, the United States government made GPS available for civilian use as well. At first, civilian GPS devices were specialized tools used in cars, boats, aircraft, and outdoor equipment for hikers, sailors, and surveyors. Then the technology started to shrink. Receivers became smaller, cheaper, and easier to build into everyday machines. The real turning point came with smartphones. Once GPS was built into the phone, location stopped feeling special. It became a habit. People opened Google Maps or Apple Maps without thinking. They used GPS to call a ride, order food, find a hotel, check traffic, share their location, or walk through a neighborhood they had never seen before. A system that began with submarines, missiles, and military strategy became an ordinary gesture, looking down at a screen and trusting the blue dot. But GPS does not only help us move from point A to point B. When a technology can locate almost anything, it starts to change entire industries. More than directions, GPS is no longer just a feature inside a map app. Once the world learned how to measure position from space, location became useful almost everywhere. On farms, GPS-guided tractors move through fields in straighter lines, helping farmers plant, fertilize, and manage land with less waste. In logistics, GPS lets companies follow trucks, ships, delivery routes, and packages as they move across cities and oceans. In aviation, it helps pilots navigate long distances and approach destinations with confidence. It also follows us in smaller personal ways. A running watch uses GPS to measure distance, pace, speed, and direction. A cycling app turns a weekend ride into a line on a map. Even geocaching, a modern treasure hunting game, turns coordinates into hidden objects waiting to be found. That is what makes GPS so unusual. A technology once designed to locate submarines, missiles, and military assets now helps people deliver pizza, run marathons, grow crops, find luggage, and meet friends in crowded places. And as the world becomes more dependent on precise location, GPS is becoming a foundation for systems still being built. The future built on position. GPS keeps improving because the world keeps asking for more accuracy, reliability, and confidence in places where signals are weak or blocked. In the future, GPS will often work alongside other systems, such as inertial navigation, which can estimate movement even when satellite signals are interrupted. That combination matters in cities full of tall buildings, tunnels, forests, and other places where signals become messy. This is why GPS is important for more than better maps. Self-driving cars need to know where they are. Delivery drones need to reach specific locations. augmented reality needs digital objects to line up with physical streets. In disasters, accurate positioning can help coordinate rescue teams when roads and landmarks have been damaged. It can also support weather forecasting and emergency planning. So the future of GPS is not just a sharper blue dot. It is a world where machines, vehicles, and emergency systems depend on knowing their place. But no matter how advanced GPS becomes, the strange thing remains. Something we use so casually depends on a vast machine above us. The giant system behind a small dot. The next time you open a map and see that small blue dot, it may feel almost too ordinary to notice. It moves when you move. It turns when you turn. It quietly tells you where you are, as if that were the simplest thing in the world. But behind that dot is a larger story. The Cold War, submarines and missiles, satellites in orbit, atomic clocks, distance mathematics, radio signals crossing space, and corrections needed because time behaves differently above Earth. GPS gives us one simple answer: you are here. To make that answer possible, humanity built one of the most complex technical systems ever folded into everyday life. We use it so casually that it almost disappears. The more familiar a technology becomes, the easier it is to forget how extraordinary it really is. Sometimes the smallest thing on your screen is proof of a giant system quietly working in the sky. If you enjoyed discovering the hidden system behind everyday things, subscribe for more stories from the secret of simple things. And if there is another ordinary object or technology you want us to explore, leave your suggestion in the comments.